Welcome to our video on data storage, where we explore the essential foundations of how computers represent and manage information. Computer memory is organized as a vast collection of circuits known as memory cells. Each cell stores a single bit, with bytes acting as the standard grouping of 8 bits. Every cell is assigned a unique numeric address, while random access memory, or RAM, allows these cells to be accessed independently in any order. When measuring memory, we often see discrepancies between binary system reports and marketing terms. This table highlights common prefixes like kilo, mega, giga, and tera, and shows how their binary values compare to their decimal-based metric approximations. For long-term, non-volatile storage, we rely on mass storage devices. Magnetic disks store data on spinning platters using tracks and sectors. Performance is primarily measured by seek time, which is the time to move the read-write head, and latency, which is the time spent waiting for the disk to rotate. Modern storage also utilizes optical and flash technologies. Optical storage like CDs and DVDs uses lasers to read microscopic pits and lands. Meanwhile, flash memory, found in SSDs and USB drives, offers high speed and durability by trapping electrons in chambers without the need for any moving parts. Understanding data organization is key. A logical record represents a natural unit of information, like an employee profile. A physical record refers to a block of data stored on a specific device location. Buffers are used as intermediary memory areas to synchronize these slower storage devices with the high-speed CPU. Computers represent text using encoding standards like ASCII and Unicode, which map characters to numeric bit patterns. Digital images are handled differently, stored either as bitmaps, which are grids of individual pixels, or as vectors, which use mathematical descriptions to define shapes and colors. To represent sound, computers use sampling, recording wave amplitudes at regular intervals, such as 44,100 times per second for CD quality. Alternatively, MIDI acts like a digital musical score, controlling synthesizers rather than storing actual sound waves. Data rates can be calculated using size, rate, bit depth, and time. Integers can be stored using 2's complement, which uses a sign bit to distinguish positive and negative numbers. Another method is excess notation, where a midpoint value represents 0. Regardless of the method, an overflow condition occurs if a calculation produces a value that exceeds the supported bit range. The binary system uses base 2 positional notation, where each position corresponds to a power of 2. Binary addition follows specific rules similar to decimal math, but carries are triggered specifically when the sum reaches 2. Let's review. Consider what determines the maximum memory addressable in a system. Compare the retrieval speeds of different storage types and practice calculating 2's complement values. Moving on to more advanced concepts, we will now cover fractional encodings and the fundamentals of data compression. Storing real values with fractions requires more than just standard integers. Systems must track the position of the radix point. Similar to scientific notation, these values are stored using a conceptual formula involving a mantissa and an exponent to define the number's magnitude. A floating point byte is partitioned into 3 key parts: the sign bit, which indicates if the number is negative or positive, the exponent field, used for scaling, and the mantissa field, which holds the actual fractional digits of the value. Normalization is crucial to eliminate redundant bit representations. By packing the mantissa and adjusting the exponent, we ensure consistency. Special cases, like the value 0, are typically hard-coded to prevent circular mathematical logic during processing. Now let's explore the fundamentals of data compression. We generally categorize these techniques into lossless schemes, which preserve the original data perfectly, and lossy schemes, which permanently discard unnoticeable details to maximize space savings. One common lossless technique is run-length encoding. It targets structural redundancy by replacing continuous repeating sequences with a simple data token and account value, making it highly effective for simple bitmap images. Frequency-dependent encoding, such as Huffman coding, optimizes space by using variable-length bit patterns. By assigning the shortest codes to the most frequent characters and longer codes to rare ones, it significantly reduces the overall file size. We also use relative and dictionary encoding. Relative encoding saves space by recording only the differences between successive data frames, while dictionary compression uses numeric pointers to reference repeated data blocks. Adaptive algorithms, like LZW, can even build these dictionaries on the fly. To wrap up this module, consider these practice problems. Test your skills by decoding floating point bytes, converting fractions, determining whether specific compression scenarios are lossy or lossless, and applying run-length encoding to a sample data stream.